So let's talk a little bit about chapter 4, which is mass, moles, and the empirical formula. So let's start off with the fundamental idea of this chapter. Particles have characteristic masses. So for example, if I draw a penny, so I know that 1 penny corresponds to 3 grams, right? So that's just an estimate for the mass of a penny, right? So then, does this look a lot like a conversion factor to everyone? Does this look like a typical equality and a conversion factor? What other way can we write this? So we know that in 3 grams, that corresponds to how many pennies? 1, yeah. So in 3 grams of pennies, there's 1 penny. Alternatively, 1 penny corresponds to how many grams? 3 grams. Okay. So, in effect, we have a way of converting between mass and the number of particles, right? Where our particles are pennies, right? So then, if we have 36 grams, let's suppose we're starting with 36 grams, and we want to go from the mass in grams to the number of pennies. How do we go from grams to pennies? What conversion factor do we use? 1 penny per 3 grams. We want our pennies on top. So we have 1 penny per every 3 grams. And that in turn gives us a total of 12 pennies. So in effect, we've converted from mass to particles, right? Okay. Now, a fundamental idea in chemistry is this idea that the same mass does not represent the same number of particles, right? Now, this can be best shown if we compare a penny to a quarter. So a quarter is substantially larger than a penny. One moment. So a quarter, so 1 quarter, one moment. So we know that in 1 quarter, let me switch out of this, give me 1 moment. So we know that 1 quarter is equal to 6 grams. So a quarter has a larger mass per particle. So then, if we look at the same 36 grams, if we're looking at 36 grams of quarters, can we figure out how many quarters we have in this mass? Yes. So we're going to take 36 grams, and we know that in 1 quarter, we have a total of 6 grams. So 36 over 6 gives us 6 quarters. And the key thing I want you to focus on is if we compare the number of particles, the number of coins that we have in these 36 grams, do we have a different number of pennies than quarters? Yes. So different particles have different masses. That's the key point I want you to keep in mind. So let's relate this back to chemistry. What does this have to do with chemistry? Why did we go through this exercise? Well, atomic mass represents the mass of an atom. Okay? The periodic table gives us the atomic masses of the elements in atomic mass units. These are called AMU or U. Now, to be really exact here, this is the mass in AMU of a single atom. This is the mass of a single atom of that element. So for example, from hydrogen, we know that the mass is equal to 1.007 AMU per every 1 hydrogen atom. Okay, so the units of atomic mass are AMU per atom. Now, what is an AMU? An AMU is a very, 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 very small unit of mass that corresponds to 1.67 times 10 to the negative 24th gram. So we know that the mass of a single hydrogen atom is equal to 1.67 times 10 to the negative 24th gram per every one hydrogen atom. Atoms have a very, very, very small mass. Does that make sense to everyone? You don't have to memorize the exact value of an AMU. What I want you to appreciate is the fact that this is the mass of a single atom. Yes?
Does it differentiate between elements, so like hydrogen is
yes.
or another element?
Yes, exactly, because we got this 1.007 directly from the periodic table and directly from the atomic mass given in the periodic table. So for example, and this is a wonderful lead in here, if, for example, we are looking at carbon, which is 12.011, let's write out what would the mass be for carbon? What would the atomic mass for carbon be in AMU per atom? 12. Yeah, we just read off this number. It's 12.011 AMU per one carbon atom. And this is where I really want you to label your units. It's not atoms of anything, it's atoms of carbon. We don't confuse a penny from a quarter, right? So we should clearly indicate what element we're dealing with. Does that make sense? Okay. So let's start using this atomic mass. Now, I really want us to have all the tools at our disposal. So in the notes is a copy of the periodic table. We're also going to be referring to a periodic table that we have from previous handouts. So let me clear out the periodic table handout from last time and just know we're going to be referring to the periodic table a lot. And what number do we care about a lot in this chapter if we're thinking about atomic masses? The atomic mass. So we're going to need the periodic table to get our atomic masses. Okay, so we have the periodic table. Let's focus on using the periodic table now. How can we use the atomic mass? So the atomic mass provides a mean to count atoms by measuring the mass of a sample. So atomic mass has units of AMU per atom. Okay, so in this question, we're asked how many atoms of sulfur are in 36 grams of sulfur. So how can we use the atomic mass to answer this question? So we're starting off with units of grams of sulfur, okay? And what is my end goal? What final units do I want to report? Atoms, okay? Okay, so just like unit conversions in the previous chapter, we write out our starting units and our ending units. Now, do we have a piece of information that relates the mass of sulfur to the atoms of sulfur? So do we have something that measures the mass of a single atom? What do we call that? Atomic mass, exactly. So let's go to our periodic table and let's go to sulfur. Let's go straight to sulfur, and you're just gonna have to give it a moment as it's snapping into resolution. So what is sulfur's atomic mass? What is sulfur's atomic mass? About 32, okay. Now, it's really important that when we figure out the atomic mass, when we look up the atomic mass, so we see 32.05. So what are the units? 32.05, what are the units for atomic mass? AMU per what? Per atom, yes. So AMU per atom of sulfur. Let me make this capital S. Okay, now that we have that established, we're going to go from grams of sulfur. So in order for us to use this conversion, what unit of mass do we need to be in? So we're starting with grams, but looking at our conversion factor, it's an AMU per atom. So what units does our mass need to be in? AMU, exactly. So we're going to go from grams of sulfur to AMUs of sulfur to atoms of sulfur. Does that logic make sense? Okay. So now that we have this outline in place, now that we have our solution map in place, we're going to execute on that. So starting off, we have 36 grams of sulfur. And my question to all of you, if we're going from grams to AMUs, what units need to be on top? AMU. So we have 1.67 times. So, yep, exactly right. So we have 1 AMU per every 1.67 times 10 to the negative 24th grams of sulfur. Okay, so this is, we're converting from grams to AMU. Now in our second conversion, we're going from AMUs to atoms. So what units need to be on top? Atoms. So in 1 atom of sulfur, we have how many AMU? 32. Okay, now we are all set to punch this into our calculator. So let's do just that. So we're going to break out our calculators and we're going to punch in 36 divided by parentheses. Everyone following so far on their calculator? And then 1.67 EE negative 24. So we've entered the first portion of this string. After your first division operation, you should get a very, very large number. Is everyone following so far? Next, we're going to divide by 32.05. And in the end, you should get 6.72 times 10 to the 23rd. Does that match what you observe in your calculator? Okay, so let's write that down. So looking at the fact that we have 2 sig figs, if we have 6.72 times 10 to the 23rd sulfur, and let me be 100% clear here, these are sulfur atoms. Looking at my initial input, how many sig figs does my initial input have? 2. So how many sig figs should my output have? 2. So I look at my last digit, I look to the right, is 2 less than 5? Yes, so then we round down and that gives us 6.7 times 10 to the 23rd sulfur atoms. And do not forget your units in this chapter because the units are critical to both solving the problem and reporting your answer. A number without units is meaningless. Does that make sense on how to use the atomic mass? So let's have you now solve a problem working together and in groups. So in this next problem, I'm asking how many atoms of nitrogen are in 140 grams of nitrogen. So take a moment, break into groups, don't be shy to talk in groups, and we'll discuss this problem in approximately 2 to 3 minutes. Yep, that's fine. Yes, there's anyone would be, even the one from also there's one president. Well, I know that. Yep, that's perfect. The numbers are all the same. So this is 14.047. Yep, looks good. Everything gone? Yep. Everything gone? Yes. That's exactly right. That's perfect. Yes, we're gonna expand. Oh, so when we say things, it can be anything.
So when you can
But that would be one mole. Mole is typically referred to counting objects. So AMU is like, so when we say things like atoms, molecules, formulas, tangible things, rather than just not AMU, but molecules. Yeah, so a mole is typically referred to counting atoms or molecules. Does that make sense? Looks good. Yep. No, this is different. So this is a lead-in to all the doctors. Yes. So I saw a lot of reasonable answers. So let's now talk through this problem. And first and foremost, let's establish what we're trying to do. We are starting off in terms of initial values with 140 grams of nitrogen. In the end, we want to report the atoms of nitrogen. Okay, so with that established, what we're going to do now is what is our bridge between grams and atoms? AMU, exactly. Okay, and how do we find our conversion factor? How do we figure out our conversion factor to go between AMU and atoms? Where do we get that? Periodic table, exactly. So let's go to the periodic table. Let's go and find nitrogen. And let's zoom in now on nitrogen's atomic mass. Give it one moment to snap into focus. So what is nitrogen's atomic mass from the periodic table? 14. Perfect. So then we're going to go to and we're going to write down that for nitrogen, we have 14 AMUs per one nitrogen atom. And I'm just going to keep this on the side for now. And let's write out our conversion factors going from left to right. So we're starting off with 140 grams of nitrogen. And do we have a way to go from grams to AMU? What units are going to need to go on top in this conversion factor? AMU. So in one AMU, we have 1.67 times 10 to the negative 24th grams. So this is one AMU of nitrogen, and we have 1.67 times 10 to the negative 24th grams of nitrogen. You'll always be given this relationship. Now, if we're going from AMUs to atoms of nitrogen, what units go on top? Atoms. So then we have one nitrogen atom per every 14 AMUs of nitrogen. And now we're ready to punch this into our calculator. So let's do just that. So we're going to take a 140 divided by parentheses. Then we're going to hit 1.67 EE negative 24. Okay, so we've completed the first step of our operation. We completed the first step, and we have 8.38 times 10 to the 25th. To complete this string, we're just going to divide by 14, which is our atomic mass. So in the end, you should get about 6 times 10 to the 24th. Does that match what you've observed in your calculator? Okay. So let's write out our response. So we have 5.98 times 10 to the 24th, and the units are nitrogen atoms. Okay, looking at our input, how many sig figs did our input have? How many sig figs did our input have? Let's be really careful here. 2. This 0 is not significant. So then, if we look at the second significant digit in our answer and we look to the right, do we round up or down? Is up. So that gives us 6.0 times 10 to the 24th nitrogen atoms. And please do not forget to include the units. Does that make sense to everyone? Okay. Let's do another example of how we use the atomic mass to solve problems. So in this problem, we know that the mass in AMU of this number of atoms of hydrogen, so in this case, we're asked, what is the mass of this many atoms of hydrogen? And as a follow-up, we're asked, what is the mass of 23 atoms of barium? So these are two separate problems, and our goal in this section is to get used to converting from atoms to mass. Okay, so let's start off with our hydrogen example. We are given that we have 2.33 times 10 to the 16th atoms of hydrogen. And our end goal is what unit? What unit are we trying to reach here? So looking at the problem, what is the mass AMU? Okay, so instead of going from AMU to atoms, we're going from atoms to AMU. So we're doing the exact same conversion in reverse. So then, do we have a conversion factor that relates the number of hydrogen atoms to the mass of hydrogen atoms in AMU? What conversion factor do we call that? Where do we get that conversion factor? So what's the relationship between the number of atoms and the mass? So do you have something that gives us the mass of a single hydrogen atom?
Yeah.
Yes. From the periodic table, we need to get our atomic mass. So we're going to go to our periodic table, and we're going to find hydrogen. And we're going to look for its atomic mass. And we've actually already seen hydrogen's atomic mass. What is hydrogen's atomic mass from the periodic table? About 1, to be approximate. Yeah. So then we know that hydrogen's mass is 1.007 AMU per hydrogen atom. Okay, so now that we have this conversion factor, if we wanted to go from atoms of hydrogen to AMU, what units will be on top? AMU, right? Okay, so we're going to take our 1.007 AMU per atom, and we're going to multiply it by the number of atoms, which is 2.33 times 10 to the 16th atoms of hydrogen. So our hydrogen atoms cancel, and we're left with units of AMU. So let's punch that now into our calculator. Does this make sense from a unit analysis perspective? Is everyone clear where we're getting these numbers from? Okay. So now let's punch this into our calculator. We have 1.007 times 2.33 EE16. And we get a number very close to what we started out with. So let's write that down. So we end up with 2.346 times 10 to the 16th AMU. Okay, perfect. Now looking at our input, how many sig figs did our input have? 3. So how many sig figs should our output have? 3. So looking at our third significant digit, if we look one space to the right, do we round up or down when we have 6? Up. So that gives us 2.35 times 10 to the 16th AMU. Perfect. So we've gone from atoms to AMU. What I want you to do now is, given this representative example, I want you to tell me, given that we have 23 atoms of barium, I'd like you to tell me the mass in AMU. I want you to tell me, what is the mass of 23 atoms of barium? So let's take a moment and let's work on this example in groups. So let's take a moment and let's try to set this up, and we'll come together to discuss in about 2 to 3 minutes. Any questions? Any questions? Everything going okay? Looks good? Okay. Any questions? And do you have a copy of the periodic table? You're welcome to pull it up on your phone. Yep, it looks good. Setup looks good. Oh, okay. Any questions? So when we're going from atoms to AMU, what units need to be on top? And so the number 137, what does that refer to? Yeah, so it has units of AMU per atom, right? So then if we have 23, not sure. Yes, exactly. Everything going okay? Yep, looks good. So I saw a lot of reasonable responses. So let's now quickly talk about this problem. So if we go to the periodic table and we look up barium in the periodic table, let's do that. So we pull up our periodic table and we find barium. What is the atomic mass of barium? Give it a moment to snap into resolution. What would someone like to tell me, if you look up physically on your own copy of the periodic table, what is the atomic mass? 137, okay? And let's be specific with our units here. Let's be very, very specific with what units we are dealing with. So we know that it's 137, and the atomic mass has units of what? AMU per what? AMU per atom. So this is the mass in AMU per atom of barium. Okay? And how many atoms of barium are we dealing with? 23. So let's plug that in. So we have 23 atoms of barium. Our units of atoms cancel, and we end up with, punching this into our calculator, 23 times 137, which gives us roughly 3,100 AMU. So let's write down this number and let's round to the right number of sig figs. So we have 3,151 AMU. Looking at our input, how many sig figs does our input have if we consider this a non-exact number? 2. So then how many sig figs should we round our output to? 2. So we go to the second significant digit, we look to the right, we see a 5. So do we round up or down? Up. So that in turn gives us 3,200 AMU. Remember, you still need to keep your placeholder zeros because this is 3,000, not 300. Yes?
Will we consider the conversion constant?
Yes, all conversion factors are considered exact because they have such a large number of sig figs that they'll never constrain the precision of your measurement.
So we will use them.
You wouldn't worry about the sig figs in your conversion factor.
Okay.
You only care about your input data sig figs. Yes.
Is it okay if we write it in scientific?
Yes, that's perfectly fine. You can also write this as 3.2 times 10 to the third AMU. That is also perfectly okay. And scientific notation is explicit in sig figs. Does that make sense so far? Oh, yes.
Is the AMU also known as molar mass?
So this is a variant of molar mass in that instead of expressing the mass in grams, it expresses the mass in atomic mass units. What we're going to do is we're going to tie this to molar mass using Avogadro's number. So this is the precursor to that. So let's now move on and let's talk about doing a 3-step conversion. This time, we are not asked to just go from point A to point B. We're asked to go through some intermediate conversion. So in this case, we're asked, what is the mass in grams of 3.4 times 10 to the 12th atoms of bromine? So when solving these sorts of problems, let's write our initial and final units. So what units are we starting out with? What are we given? Atoms. So we know that we have 3.4 times 10 to the 12th atoms of bromine. And our end goal is to report what? Grams. So we want to report grams of bromine. Now, inevitably, if we look at our conversion factors, what stepping stone unit will we have to go through? AMU, typically. Now, for those wondering, why are we going through AMU? If we want to go from atoms to a unit of mass, what conversion factor do we currently have access to? What conversion factor have we been using throughout this section? The periodic table, which gives us, what do we call that? Atomic mass, exactly. So we're using the atomic mass. So the atomic mass is our vehicle to go from atoms of bromine to the mass of bromine in AMU. And if we look up the periodic table, if you zoom in on bromine, I want us to do this now. Just take a look at the periodic table. What is bromine's atomic mass? 79.9. Okay. Of course, you'd write out all the significant digits found in the periodic table, but you just want to get in the habit of going to the periodic table and reading the atomic mass, which is the number below the symbol. Okay, so now that we have the atomic mass in hand, this is 79.9 AMUs per 1 atom of bromine. We're now ready to set up our conversion. So if we're going from atoms to AMU, what units need to be on top? AMU. So we're going to write out 3.4 times 10 to the 12th atoms of bromine. And we know that we have how many AMU? How many AMUs do we have per atom? 79. So we have 79.9 AMUs per atom of bromine. Okay, and to go from AMU to grams, do we have that conversion factor? Do we know a way to go from AMU to grams? Are we given that? Yeah. And when we do this conversion, what needs to be on top if we're going to grams? Grams. So we're going to write 1.67 times 10 to the negative 24th grams per every 1 AMU. And if we punch this into our calculator, let's do just that. So we have 3.4 EE12 times 79.9, okay? And then times 1.67 EE negative 24. And we should get what is a very, very, very small mass of about 4.5 times 10 to the negative 10. Does your calculator match that? Okay. So let's write that down. So we have 4.5 times 10 to the negative 10th grams of bromine. I always include my final unit labels. Does that make sense to everyone? Did I do a good job rounding my sig figs? Does our output have the correct number of sig figs as our input? Yes, so we're good to go. So now let's have you solve one of these problems. So this time we're given an element has a mass of 3.2 times 10 to the second AMU for 15 atoms. Now, as this is a new problem, we're going to do this first type of problem together. Okay? So looking at this problem, we are given what pieces of information? The mass. Yep. We know that the mass is equal to 3.2 times 10 to the second AMU. Are we also given the number of atoms that we've measured the mass of? Yes. So we also know that our number of atoms is equal to 15 atoms. So do we have enough information, if we wanted to calculate the atomic mass? Yes. So looking at the atomic mass, so thinking about this just from a unit perspective, the atomic mass is what set of units? What over what? What are the units for atomic mass? AMU, right? Over atoms. Okay, so we have the mass in AMU, we have the number of atoms, we have all the information we need, right? So let's just plug that in. So we have 3.2 times 10 to the second AMU divided by 15 atoms. Okay, and that gives us an atomic mass. Let's punch that into our calculator. So we have 3.2 EE2 divided by 15. And that gives us an atomic mass of 21.33 AMU per atom that we round to how many sig figs? How many sig figs do we round to? 2. So that gets rounded to 21 AMU per atom. Now, just taking a tour of the periodic table, would someone like to tell me what element most closely matches that mass? What element most closely matches a mass of about 21 AMU? Just allow it one moment to snap into focus. What was that? Yeah, neon would be a reasonable fit. We don't quite have the level of precision necessary to distinguish between neon and sodium, so it would be reasonable to say this may be a sample of neon. So I'm going to write this as neon with a question mark. If we wanted to get a more exact element assignment, we want to make sure our atomic mass exactly lines up with the mass in the periodic table, because we're looking at such a large number of atoms. Okay, now that we've discussed how to calculate the atomic mass, I'd like you now to take a try on the following problem. So we're given that we have 1.5 times 10 to the 25th atoms, and they have a total mass of 398.7 grams. So I'd like you to tell me the atomic mass. Please make sure you have units of AMU per atom. And then I'd like you to tell me what element is this species. What is the element that corresponds to that atomic mass? So take a few moments, work on this. Don't be shy to discuss this in groups. And then we'll come to you to discuss in about 2 to 3 minutes. Any questions? Any questions? Everything Everything going okay? Everything going okay? Any questions? Okay. Everything going okay? Yep. That seems reasonable. May I see your work for it? Ah, okay. Well, try writing out the setup just so I can take a look at it. And that way. Yep. Exactly. Yep, exactly. Everything going okay? So the only difference from the previous problem, instead of being given a mass in AMU, what mass do we have? Grams. Can we get to AMU from grams? Yep. Everything going okay? Okay. Everything going okay? Everything going okay? So then, comparing to the previous problem that we solved, instead of being given the mass in AMU, we're given the mass in grams. But can we get to AMU from grams? Do we have that conversion? Yeah. And once we do that, then we're at home free. So the mass in the periodic table is given in terms of AMU per atom. So then, since we're starting with a mass in grams, can we go from grams to AMU? Because then once we have the mass in AMU, we already have the number of atoms. Does that make sense? Everything going okay? Yeah. Yep, exactly. Everything going okay? May I see your yourself? Yep, exactly. Everything going okay?
Yeah. So,
May I see your yourself?
yeah, just looking at the conversion.
Ah, okay. Is everyone okay for us to discuss this problem now? We'll be doing plenty of examples on this, but just to give everyone a little bit of guidance, I saw a lot of reasonable setups. Everyone was on the right track. So if we need our atomic mass to be in AMU per atom, our first order of business is to look at our mass and say, is our mass in units of AMU? Is our mass in AMUs? No. So we have 398.7 grams, and we want to go from grams to AMU. So let's do that. So 398.7 grams. And if we want to go from grams to AMU, what units need to be on top? AMU. So we know that 1 AMU corresponds to 1.67 times 10 to the negative 24th grams. So in effect, we've converted from grams to AMUs, and let's punch that into our calculator. So we have 398.7 divided by 1.67 EE negative 24. And that gives us a very large mass in AMUs. So let's write down this number, remembering that we're not rounding until the end. So we're writing down all of these digits. So that gives us 2.387425 times 10 to the 26th AMU. Quite a large number. Okay, now that we have our mass in AMU and we have our number of atoms, can we plug that in and solve for our atomic mass? Yes, so let's do just that. Okay, so we have 2.387425 times 10 to the 26th AMU divided by how many atoms do we have? 1.50, yep. So we have 1.50 times 10 to the 25th atoms. So if we're calculating our atomic mass, we can now punch this into our calculator. Now, if you've been leaving your calculator as I have, you already have your mass inputted. This is why I like to set up my calculations first and then execute. So that way I'm not having to re-enter this giant number into my calculator. Okay, so now I'm going to divide by parentheses 1.50 EE25. And that in turn gives us a reasonable number of 15.916. So let's write down our final output. So we have 15.916 AMU per atom. And now looking at our input, how many sig figs do we need to round our output to? 3. So looking at all of our measurements, we see we have 3 sig figs on the bottom. So we need our answer to be rounded to 3 sig figs. We look to the right, is 1 greater than or less than 5? Less than. So then that in turn gives us 15.9 AMU per atom. Now, if you look around at the periodic table, let's now try to find a match for this atomic mass. So let's try to find a match for this atomic mass. So give it a moment to snap into focus. Take a look at your own periodic table. And where do we see a mass of about 15.9? Somewhere around 16. Oxygen, yep. So if we look in the periodic table, we see oxygen is a pretty good match. Does that make sense to everyone, how to solve these types of problems? Okay. So now let's write our final assignment down. So we've assigned this to be oxygen. Perfect. Okay. Let's now get to a more common way of expressing mass in chemistry. Let's move on to a more common way of expressing mass. And ultimately, in chemistry, we aren't typically dealing with just single atoms, right? We're often dealing with, and reactions involve, molecules. So the molecular weight, otherwise known as the molar mass, is the entire mass of our molecule, okay? So the mass of a molecule, or the molecular weight, is the sum of the atomic masses of the atoms in that molecule. So essentially what you're going to do when you're calculating the molecular weight is you're going to take the mass of your atom of a given element, and you're going to multiply by the number of atoms of that element. So we're just adding up all of our masses, just like dropping weights on a scale. So to showcase how this works, we're going to go to sodium sulfate. So Na2SO4. So I always like to draw a picture when I'm starting out with this. So let's first read our formula and let's figure out how many atoms of each element do we have. So looking at Na2SO4, how many sodium atoms do we have? How many Na symbols should I draw? 2. So I'm going to draw 2 sodium symbols, okay? Okay, let me switch to a different pen color. How many sulfurs do I see? Just 1. Okay. And then finally, how many oxygens do I see? 4. We're not drawing them with any respect for the actual connectivity of atoms for now. We're just focusing on counting atoms. Okay, so now that we have all of our atoms in place, we see, first and foremost, we have 4 oxygen atoms. And recalling from our previous discussion, what is the mass of oxygen? What is the atomic mass in the periodic table? If we go to the periodic table, what is it? 16. So we have 16 AMU per oxygen atom. So we've taken our number of oxygen atoms times the mass in AMU per atom. Okay? Let's do the same process since we're adding up the mass of all of our atoms of each element in this molecule. How many sulfur atoms do we see? 1. So we have 1 sulfur atom. And now we're going to have to go to the periodic table. Now we're going to have to go to the periodic table and let's find the atomic mass of sulfur. So if we go to the periodic table, we go to sulfur. Would someone like to volunteer? What atomic mass do we see in the periodic table? Yep, about 32.06. So then let's now go back and let's write that down. So we have about 32 AMU per sulfur atom. Finally, we're going to repeat this process for sodium. So we have how many sodium atoms? 2. So we have 2 sodium atoms. And we know that the mass of sodium, looking at the periodic table, is about what? Yeah, it's about, so you get 22.9. We're going to round it to 23 just for this demonstration. So we have 23 AMU per sodium atom. So if we punch out all of these numbers into our calculator, we're going to get 64 AMU, 32 AMU, and 46 AMU. So let's now add these numbers together. Let's add these together into our calculator. So we have 16 times 4. So here's our 64 plus 32. And then finally, plus 23 times 2. And in the end, if we add up all of our atomic masses, we get a molecular mass or a molar mass of 142. Now, what are the units for this 142? So AMU, because our mass is in AMU. And now, what is this the mass of? What did we measure the mass of? A molecule. So instead of AMU per atom, it's AMU per molecule. So this is AMU per molecule of, let's be specific here, of sodium sulfate. There we go. So this is how you calculate, and let me zoom up a little bit. So this is how you calculate the molar mass or molecular weight, and the units are AMU per molecule. Does that make sense? Okay. Now, just as a review, the number of each atom of each element is given by the molecular formula coefficients. As we've discussed earlier, we were able to see from the molecular formula subscripts that there were 2 sodiums, 4 oxygens, and 1 sulfur. So this is why we discussed counting atoms last chapter. So that way you're used to reading formulas so you can calculate the molar mass quickly and efficiently. Any questions on this idea? Okay. So what we're now going to do is we're going to start looking at not just single atoms or single molecules, but we're going to try to look at our masses in terms of groups of molecules, groups of atoms. And our goal in this section is to find a way to have a unit of measurement that allows us to measure out quantities, masses on a scale, and relate that to the number of atoms in that sample. So we're trying to connect our macro scale, masses we can weigh, to a number of atoms at a micro scale. That's the goal of this. So we know that the masses of atoms and molecules are small. And when you go to a balance, your balance doesn't go to 10 to the negative 24th grams, right? We deal with masses on the scale of grams, kilograms, milligrams. So we're going to look at the mass of a group of molecules or atoms. Now, to really help us grasp this analogy, to help us understand the concept of a mole, let's first think about how we count eggs. Okay? We count eggs in dozens, right? You can buy a dozen eggs at the store. And we know that there are 12 eggs in a dozen, right? So then, we know in general there are 12 things in a dozen. So for example, if I say 1 dozen calculators. How many calculators am I referring to? 12. I'm referring to 12 calculators. And now this is really cool because we can actually do these conversions really quickly because we're so used to the idea of a dozen. If I told you we have 3 dozen candies, I expect many of you will be able to tell me what number, how many candies do we have if I have 3 dozen? 36, right? We're really fast at doing these relationships and figuring out the amount in a dozen. And not just 1 dozen, and 2 dozen, 3 dozen, however many dozen candies we have, we know that a dozen represents 12, right? Now, in chemistry, we're going to count a very large number of objects. So in this case, instead of using a dozen atoms, we're going to count moles of objects. So what does a mole represent? Instead of 12, a mole represents 6.02 times 10 to the 23rd. A very, very large number. So for example, if we're filling in the blanks for this idea that 1 mole is 6.02 times 10 to the 23rd things, a mole of atoms is 6.02 times 10 to the 23rd atoms. Does that make sense? So instead of 12, it's this large number. We call this number 6.02 times 10 to the 23rd Avogadro's number. And it's often abbreviated as NA. The other major way that we deal with moles is if we're looking at a mole of molecules, that corresponds to how many molecules? What does a mole represent? Yep, Avogadro's number, 6.02 times 10 to the 23rd molecules. Just to make sure we're still on the same page, 1 mole of sodium chloride corresponds to how many formula units? Remember when we discussed formula units, what did I tell you to compare formula units to? So we're saying formula units. What's another way of talking about formula units? Not quite atoms, since we have two different atoms. So what do we, instead of atoms, you're on the right track. What do we regard formula units as equivalent to? Components. What's our formal way of talking about 2 or more atoms bonded together? Molecules, exactly. So when we think of moles of ionic compounds, we often talk about groups of ionic molecules in terms of formula units. So if we said a mole of sodium chloride, a mole corresponds to how many molecules, how many formula units? Yep, 6.02 times 10 to the 23rd. When you see the word formula units, I just want you to always remember it's often treated in calculations the same way as molecules. Okay, so the key thing, a mole is used to count large numbers of atoms, molecules, formula units. Now, we've used moles as a unit of counting because it allows us to express our atomic masses on a scale that we handle on a day-to-day, express our masses in terms of grams. So it allows us to relate quantities we measure in the lab to the actual number of atoms more easily. So if we want to get the mass of a mole of atoms or molecules in gram per mole, many of you are probably more familiar with atomic masses and molar masses in gram per mole. All you need to do is multiply the mass of a molecule by Avogadro's number. So let's do this for a very, very simple molecule. Let's do this for a very, very simple molecule, H2. So if we break out our periodic table, let's do this calculation. What is the mass of just a single hydrogen atom in AMU? Yeah, about 1. So we have about 1 AMU, okay? 1 AMU per hydrogen atom. Okay, and how many hydrogen atoms do we have in one H2 molecule? How many atoms do we see in H2? 2, exactly. Okay, so currently we have the mass in AMU per molecule. Okay, so currently we know that there's 2 AMU per 1 H2 molecule. Okay? Now, what we're going to do is we're going to convert AMU per molecule into gram per mole. So let's show how we'd accomplish this conversion. And it's going to seem like we're doing a lot of work to get back to where we started. So starting off, if we have AMU per molecule, we're going to first go to gram per molecule, and then finally to gram per mole. So this is our conversion map. These steps are technically interchangeable, but this is just how we're going to do it together. So let's write out our initial input. So we have 2 AMU per H2 molecule. And my question to all of you is, if we want to go in our first conversion from AMU to grams, do we know that conversion? Can we go between AMU and grams? Yes. And what goes on top if we're going to gram? Yep. So we're going to go to grams. And more specifically, I heard it from Victoria, 1.67 times 10 to the negative 24th gram per AMU. The key thing, if you know where to place your units, the number associated with that unit will follow. Okay, in our next step, we're going from 1 over molecule to 1 over mole. Now, if we want moles on the bottom, oh, whoops, this is, oh, yep. So if we want moles on the bottom, where do we need to have moles in our conversion factor? So if we want moles on the bottom in our final answer, where do we need to have moles in our conversion factor? On the bottom, right? You want your units to be in the same location as they are in your final output. So then, in 1 mole, that corresponds to how many molecules? Yep, exactly. So let's plug that in. 6.02 times 10 to the 23rd molecules. Now, we're going to enter this into the calculator, but I'm going to tell you right now that you're going to get about 2 gram per mole. And this is why it's really brilliant how Avogadro's number and the atomic mass in AMU were designed. Because these two numbers, when multiplied together, are equal to 1, approximately. So let's show that by punching this into your calculator. So we're going to take 2 times 1.67 EE negative 24 times 6.02 EE23, and we get a mass of roughly 2 grams per mole. So it seems like we did a lot of work, but the goal of this demonstration and the entire purpose of this demonstration is to show that the molecular weight in gram per mole is about equal to the molecular mass in AMU per molecule. So you can read the periodic table and get masses in units of gram per mole. Does that make sense to everyone? Okay. So we have a beautiful new tool available to us. Does that make sense? Okay. So let's now talk about our general solution map. How can we use this molar mass? And from now on, when you see the words molar mass, I want you to think gram per mole. So the molar masses from now on, we're going to focus on gram per mole. Okay? Because we handle masses in terms of grams more often than AMU. So in this solution map, I just want to walk you through it because it's really useful and something that if you want something to memorize and write down on your paper at the start of an exam, this is a great place to start. So what I'm showing you is how to go between different units of measurements, and we're going to talk about what conversion factors to use. So first and foremost, let's color code this. I always like to use color. So if you see an arrow in blue, you're going to divide. You're going to divide by our conversion factor. If you see an arrow in red, that means you're going to multiply. Okay? So if we start off with the number of atoms or molecules or formula units, we can go from atoms, molecules, or formula units to moles if we divide by Avogadro's number. So we're going to divide by Avogadro's number to go from atoms to moles. Okay? So that's one way. If we wanted to go from moles to atoms, the opposite direction, we're going to multiply. So we're going to multiply by Avogadro's number. Does that make sense to everyone so far? Now, we're going to shelve this middle conversion for now. We're just going to leave this one alone. We'll talk about that in a moment. Let's now look at what would happen if we wanted to go from moles to mass. So to go from moles to mass, we'd multiply by our molecular weight or our molar mass. Does that make sense? If we wanted to go from mass to moles, we'd divide by our molecular weight. You often see molar mass expressed as MW or MM. Both are common and both are accepted. Okay, so we have a map to go between atoms, moles, and grams. So now let's apply this solution map from the perspective of unit analysis. So we're asked what mass of carbon dioxide is found in 1.55 moles of carbon dioxide. Okay, so what are we starting off from? What units are we starting off from? Moles. So we're starting off from moles of CO2. And what do we want to report in the end? Mass. And whenever you hear mass from now on, you think grams. So we're going to go to grams of CO2. If on an exam you saw this question and you gave me the mass in AMU, I'd be fine with it, but I want us to get in the habit of reporting grams from now on. Okay, so then starting off with 1.55 moles of CO2, what units do we need on top? grams. So we need something of the form grams of CO2. And then what, in order to cancel out these moles, what units do we need on the bottom? Moles. Okay. So we need something of the form grams of CO2 per mole of CO2. And that just happens to match our molecular weight. So if you're looking at the solution map and wondering how this all fits in, you're wondering, how does this solution map help me? I'm starting from moles, right? I want to get to grams, right? So what does my solution map indicate I need to do? I need to take my molecular weight, and do I multiply or divide? Multiply. And as we see, when we set up our problem using unit analysis, we are multiplying by our molecular weight. Now, with that said, what do we need to calculate now? Molar mass, molecular weight. So let's break that down. So for CO2, let's now read off our masses from the periodic table. Let's read off our masses. For carbon, what is the mass of carbon? 12, okay. So we have about 12 gram per mole. So that's carbon. Let's now change colors for oxygen. So for oxygen, what is oxygen's atomic mass? 16. So we have 16 gram per mole. And then how many oxygen atoms do we have? 2. And if you punch this into your calculator, you get 44 gram per mole. So what do we input for our molar mass? 44. Okay. Punching that into our calculator, we have 1.55 times 44. And that gives us 68.2. So moles cancel, and we report out our final units as 68.2 grams of carbon dioxide. There we go. Does that make sense to everyone? Does this molar mass calculation seem familiar to everyone? Would everyone be comfortable doing this on their own? Where did we get these masses from again? Just to make sure. Periodic table. And remember, you can just read the number straight from the periodic table, except you put units of gram per mole. That's what we've shown in the past exercise. So what I want us now to do is let's try to showcase a conversion going the opposite direction. So I'm going to help us along here. And in this case, we're asked how many moles of carbon dioxide are there in 10 grams of carbon dioxide. So this time we have the grams of carbon dioxide, and we want to go to the moles of carbon dioxide. Okay, so before we deal with unit analysis, let's just take a look at our solution map here. If we wanted to go from grams to moles, what does our solution map indicate? What are we're going to divide by what? The molar mass, exactly. So then let's do just that. So we have 10 grams of carbon dioxide. In the end, what units need to be on the top? Moles. So in 1 mole of CO2, we have how many grams? Did we already figure that out? 44. Yep. So all we have to do now is punch this into our calculator. So we have 10 divided by 44, and that in turn gives us 0.227. Now, we need to be really careful here. So this is moles of CO2. And my question to all of you is, so taking a look at this problem, how many sig figs does my input have? 1. So how many sig figs should my output have? 1. So this would best be written as 0.2 moles of CO2 because we rounded down. Does that make sense? So what I want us now to do is to do a moles to mass conversion for a species that's atomic. So you don't have to worry about the molar mass calculation just yet, but I just want to check that you can do a mass to mole conversion. So I'd like you to tell me how many moles of iron are in 33 grams of iron. Everything going okay? Everything going okay?
I'm not sure if I find the grams for iron.
Do we know the mass of iron?
Yes.
Yes.
Oh, so it's just that?
Yep.
Um,
Your initial input mass is given, but the conversion factor, the molar mass, is just from the periodic table.
okay.
Everything going okay? Everything going okay? Yep, looks good. Everything going okay? Okay. Everything all set? Yep, looks good. Yep, looks good. Oh, just check your sig fig. Otherwise, it's good. So, perfect. I see a lot of reasonable responses so far. So let's highlight that. So we have 33.0 grams of iron. That's what we're given. And in the end, we want to report the moles of iron. So, in order to accomplish that, we're going to need to go to the periodic table and we're going to need to find our molar mass or our atomic mass. So what is the molar mass of iron in the periodic table? Yeah, about 55.5, right? Let me go to the exact periodic table and let's read off an exact number here. Give it one moment to snap into resolution. Oh, my bad, it's 55.85. Okay, perfect. Okay, perfect. We have that noted. So 55.85. And remember, we have the liberty to say gram per mole of iron. We don't have to worry about AMU per atom anymore. Okay, perfect. So given that we have 33.0 grams of iron, what units will we want on top in the end? Moles. Okay, so we know that we have 1 mole of iron per every 55.85 grams of iron. And all we have to do now is punch that into our calculator. 33.0 divided by 55.85, and we get 0.59086. So we have 0.5908 moles of iron. Now let's take a look at our input. Let's take a look at our input. How many sig figs does our input have? Is this 0 significant? Yes. So how many sig figs in total do we have? 3. So then how many sig figs should our output have? 3. So we're going to look at this 0, look to the right. Do we round up or down? Up. So we end up in the end with 0.591 moles of iron. Just always keep in mind to be careful with your sig figs and you round at the end. This is a great stopping point for the end of today's lecture. We'll continue on next class session with more involved examples.